Department, IIT Kanpur. I have done my undergrad in ETC department, Jadavpur University. And today I will be going to present my paper, which is entitled SRR Loaded Antipodal Vivaldi Antenna for UWB Applications with Tunable Notch Function. And I have done this work under the supervision of Dr. Kumar Srivastava in Electrical Engineering Department, IIT Kanpur. So in the first two slides, I will be just briefly going over the basic design issues of UWB antenna and why I am focusing on designing band-notched UWB antenna. So ultra-wideband systems, as mentioned by my previous speaker, encompass usually the frequency range over 500 megahertz. But FCC specified UWB range, where most of the UWB antennas are designed nowadays, cover the frequency range 3.1 to 10.6 gigahertz, and these UWB systems can support high data rates with low power consumption, and they are mainly used for short-range indoor communication systems, medical and military applications, and characterized by these high impedance bandwidth, radiation pattern stability, and miniaturization along with low manufacturing cost. The problem which I am addressing in this particular work is the problem of electromagnetic interference due to the existing narrowband communication systems, which some of the examples are shown here, like WiMAX, WLAN, and X-band satellite communication links. So for tackling these issues, one approach would have been integration of external band stop filters to achieve the band rejection, but actually it increases the system complexity and size. So modern day researchers have mainly resorted to the approach of embedding parasitic strips or slots of different shapes in the radiating element or ground plane of the antenna system. And also another fact is that many ultra-wideband applications require more than one notch band, so use of mutually non-interacting band notch elements is required. In this particular work, I have used reference antenna as the planar antipodal Vivaldi antenna. Actually, most of the works use these ultra-wideband monopoles, and later on, actually, this work was done initial phase of my MPhil thesis. So, when I communicated here, later on I shifted to those designs, but currently this paper is on this planar antipodal Vivaldi antenna, which have the properties like high directivity, low cross polarization, and broad bandwidth. And one point is that this particular paper that I mentioned, they have designed quite a small-sized ultra-wideband Vivaldi antenna. So I have used their concept and designed this particular reference UWB antenna on FR4 substrate, which can be easily fabricated later on. To tackle the EMI problem, I have employed this split ring resonator. Very common structure which is used as in designing negative mu metamaterials, but in this case we are using only a single resonator, so no metameter concept is coming here. Here it is only acting as a parasitic sub-wavelength high quality factor resonator, and its resonance frequency can be easily determined by two-port CPW or microstrip line analysis. So we have targeted in this particular work the WLAN application band, which is ranges between 5.15 to 5.85 gigahertz. So the dimensions, as mentioned here, are tuned such that it operates as a resonator in that particular band. And next, another point is that where to place this SRR with respect to the reference antenna. So here I have shown the result corresponding VSWR versus frequency curve for three different positions. As we can see that for the position 1, which is shown by the dotted black line, here although we are presenting the split ring resonator behind this just beside this arm, but not much rejection is occurring. Whereas in position 2, we are getting a very good VSWR characteristics throughout the band, except at the WLAN band, which is within the 5 to 6 gigahertz range. In position 3, when you are moving the SRR even further, then it is disturbing the antenna radiation or the impedance matching at the higher frequencies. So one question can arise that why this kind of phenomenon is occurring, what is so special about that region. So if we just plot the surface current density vector over the antenna, we can see that the magnetic coupling to the SRR means if we can plot the H field in the substrate, then we will see that the magnetic coupling due to the SRR will occur in round about that position. So after optimizing that, by parametric optimization, no other issues, by some parametric optimization, we have fixed that particular position, and these two are the dimension, means position parameters with respect to the antenna structure. And this is the comparison between the frequency versus VSWR versus frequency for the reference and the proposed SRR loaded antipodal Vivaldi antenna. And for any antenna system, we have to see that whether sufficient rejection is occurring by plotting that peak realized gain over the frequency. And all the simulations have been done in unsolved HFSS. We have got the gain for different frequencies and plotted for the reference and proposed antenna over the UWB band, which is 3 to 11 gigahertz. And as we can see that for the proposed antenna, the peak realized gain is falling at the position where we have designed the notch band, but it's round about the same in the other frequency regions. And in this particular slide, just to observe what is actually happening in the system, we have plotted the surface current distribution on the antenna at the notch frequency, which is around 5.56 gigahertz, which is in the middle of the WLAN band. And next, I have plotted the radiation, the surface current on the antenna at the radiating frequencies, which are at the 4 gigahertz and 8 gigahertz. And as we can see that at those frequencies, the antenna arms are smoothly radiating, although some current is going to the SR, but that is not affecting the radiation characteristics of the antenna. And finally, by comparing the gain patterns of the antenna, 3D gain patterns I have plotted directly from the HFSS. For the reference and the SRR loaded antenna, we can observe that at the radiating frequencies, the gain patterns of the antenna, that is at 4 gigahertz and 8 gigahertz, that is not much affected. And finally, to complete this, we have simulated the two antenna analysis, two antenna setup. And since the Vivaldi antenna is mainly radiating in that particular region, means along that axis of the Vivaldi antenna, so we have placed this antenna in this configuration, but other configurations could have been used. And we have plotted the resulting S21 and the phase of the S21 at these two frequencies. And we can observe that for the proposed antenna system, we are getting a big dip at the S21 magnitude characteristic in the desired region. And so finally, I would like to conclude that in this particular work, an SRR loaded antipodal Vivaldi antenna having ultra wideband characteristics with notch band in the WLAN frequency range has been designed. The impedance bandwidth and the far field characteristics of this antenna has been investigated by HFSS simulations, and the proposed antenna is low profile and designed to use in a low cost FR4 substrate. And here the band rejection property is basically achieved by using the rectangular SRR element. And by extending this concept in this paper, we can also design multiple band notched antennas for ultra wideband applications. And these are the references that I have used in this particular work, and thank you.
Very good. You're very fast.